Let's start with problems based on power engineering. So now we will discuss the problems based on power engineering. Power engineering. So here I will give some of the problems and I will show how we can solve this problem for our better understanding. So let's take a problem. First, I am writing the problem. Steam at 20 bar, steam at 20 bar, 360 degrees centigrade, 360 degrees centigrade is expanded in a steam turbine in a steam turbine to a pressure of zero point 0 at bar. It then enters a condenser where it is where it is condensed to saturated liquid water to saturated liquid water liquid water. The pump feeds back the pump feeds back the water into the boiler. The water into the boiler. Now we have to find out A. Assuming ideal processes, find per kg of steam the net work and cycle efficiency. Find per kg of steam the net work and the cycle efficiency For B part, if the turbine and pump have pump have each 80% efficiency, find the percentage reduction in the network and cycle efficiency. Network and cycle efficiency. So for this problem, we have to consider the two cases. First, we will deal with the ideal process, and second, we will deal with the actual process with 80% pump and turbine efficiency. So now we have to take some of the data from the steam table. So now let's solve this problem. So from steam table, before going into the steam table, I will first draw the TS diagram. So on y-axis I am having T, on x-axis I am having entropy, and this one is the dome. So I will show the both process, ideal and the actual process with 80% of pump and turbine efficiency. So now for this process, we are at point 1, and in ideal process After expanding in turbine, we are coming at 2s, and 2s we are entering into the condenser, and at point 3 we are leaving the condenser. Then 3 to 4s, that is our ideal pump work, and then 4s to 1, that is a heating or heat addition in boiler. So this one we are having at a temperature 360 degrees centigrade, and this pressure, suppose we are having P1, that is 20 bar, and this one P2 we are mentioning 0.08 bar. So this one is a typical ideal process. So I will write here the ideal process will be 1, 2s, 3, 4s, 1. Now we have already discussed in the real scenario there will be a losses like piping losses or losses in turbine and pump, but we are not considering the piping losses. We are just considering the losses in turbine and pump. So if we consider the losses in turbine and pump, so here in turbine 1 to 2s, that is isentropic expansion, but every process in the world is uh, having greater entropy change. So the entropy will increase if we go from 1 to 2. So the curve will be coming like that. So 1 to 2, that is a real process in steam turbine. Similarly, 3 to 4s we are having constant entropy, that is ideal, but in reality there will be a increase in entropy. So here we are having 4. So now the actual process I can say 1, 2, 3, 4, 1. That is our actual process. So this one is the representation of the ideal and the actual process on TS diagram. So now let's take some of the values from the steam table. So from steam table at enthalpy at 1 H1, that is at 360 degrees centigrade 20 bar, we are having 3159.3 kilojoule per kg, and entropy at the same point will be 6.9917 kilojoule per kg Kelvin. Similarly, H3 is nothing but the uh, water saturated water at zero point 0.08 bar. So we are having the saturated water enthalpy 173.88 kilojoule per kg, and at S3 the entropy is 0.5926 kilojoule per kg. So these values I am taking from the steam table, but in GATE they will provide either the direct value or they will give the table. Now we have to consider the latent heat at 0.08 bar. So we can say that is HFG P2 at pressure P2. So we are having 2403.1 kilojoule per kg. Whenever I will write HFG means it's a difference of Hg and Hf. So and P2 means at pressure P2, that is 0.08 bar in our problem. So here HFG at P2 is 2403.1 kilojoule per kg, and similarly the Hg here at pressure P2 is 8.2287 kilojoule per kg Kelvin. Here the specific volume of water at pressure P2 is 0.001008 meter cube per kg, and SFG at P2 is 7.6361 kilojoule per kg Kelvin. So now if you see the process 1 to 2s, so the entropy at 1 and 2s will be same because 1 to 2s is isentropic expansion. So I can write S1 equals to S2s equals to 6.9917. So we know as S2s we can write S2s we can write SFP2 plus X at that 2s equals to SFGP2. So now S2S we are having same S1 that is 6.9917. SFP2 we are already having this value that is 0.5926 here, that is 0.5926 plus S, and SFGP2 we are having 7.6361. So by this way we can calculate X. So X will be 0.838. So now we have already calculated the quality of steam at point 2s, that is 0.838 at state 2s. So now we can easily calculate the enthalpy at state 2s. So now we are interested in enthalpy at state 2s. So that is H2s, and according to the formula HFP2 plus XHFGP2. So if we put all these values, that is 173.88, we have the value of X 0.838 into HFGP2, it will be 2403.1. So H2S we will get 2187.68 kilojoule per kg. So by this way we can get the enthalpy at state 2s. Now for A part we have to calculate pump work. So pump work, if you see the diagram, pump work is from 3 to 4. So for ideal process it will be from 3 to 4s. So we are dealing in the ideal process in part A. So the enthalpy difference from 4s to 3. So we can, if we have the enthalpy difference, then we can easily calculate work done, and with the help of VDP also we can calculate the work done. So now for VDP, it is specific volume of fluid at pressure P2 and pressure difference P1 minus P2. We can easily calculate the WP. So as per as steam table, that is VFP2 is 0.001008 into this difference P1 minus P2, it will be 19.92. The difference will be 19.92 because we are having this 20 bar P1 and 0.08, that is 19.92. We have to convert because these pressures are given in bar, so we are converting into kilonewton per meter square. So this value will come 2.008 kilojoule per kg. So by this way we can calculate. Remember one thing, whatever the units you are taking, you should be consistent. Like suppose if you want a work done in kilojoule per kg, then the specific volume will be in meter cube per kg, and this pressure will be in kilonewton per meter square. So remember these things. So now We can get the value of H4S from here, that is coming 175.89 kilojoule per kg, and Wt for ideal process H1 minus H2S. So Wt we can calculate H1 we are having 3159.3, H2S we are having 21 at 7.68. So Wt we can calculate, it is coming 971.62 kilojoule per kg. So here we are having the value of H2S, here we are having the value of Wt, this pump work. By this Wt we are having H4S. Now we are having Wt, that is 971.62. So now we will calculate net work. Net work done is nothing but turbine work minus pump work. Because turbine is delivering work and pump is consuming work. So Wt minus Wp, so 971.62 minus 2.008, it will come 969.61 kilojoule per kg. So now we calculate Q1 heat addition, that is H1 minus H4S for ideal process. So 3159.3 minus 175.89. So Q1 we will get 2983.41 kilojoule per kg. So that is our Q1. So now we are having W net and Q1, so we can calculate efficiency. We can calculate efficiency, that is efficiency of ideal cycle. So now 969.61 divided by 2983.41. So it will come around 0.325, or we can say that 32.5%. So that is for part A. Now in B part we have to consider the actual process in which the turbine and the pump is having 80% efficiency. So I can write efficiency of pump is 80% and efficiency of turbine is also 80%. So now we have already calculated the turbine and pump work for the ideal process. So now the actual process, the pump work will be whatever the ideal process work done is 2.008. We have to divide with 0.8. So we get pump work for actual process is 2.51 kilojoule per kg. Similarly, for turbine, we are having for ideal process 971.62, but in ideal process due to 80% efficiency it will produce less work, so it is coming 777.3 kilojoule per kg. So this one is Wp, this one is Wt. So now we can calculate W net. W net in actual process will be same Wt minus Wp. So 777.3 minus 2.51. So it will come around 774.8 kilojoule per kg. So by this way we can calculate the net work done. Now let's calculate percentage reduction in work output. Now we are interested in percentage reduction in work output. Work output. So percentage reduction in work output, we are having actual work done. We are having the W net for the Yeah, we are having W net for actual cycle, W net for ideal cycle. So for percentage reduction in work output, W net for ideal cycle, that is 969.61, minus W net for actual cycle 774.8, divided by W net for ideal cycle, that is 969.61, into 100. So the percentage reduction in work output will come 20.1 percentage. So now we are having enthalpy at all points, but for heat addition in actual process we are interested in H4. So H4, in that case I can calculate by 173.88 plus 2.51, so it will come H 176.39 kilojoule per kg. Now I can calculate Q1, that is heat addition in actual process, that is nothing but H1 minus H4. H1 will come H1 minus H4. So H1 minus H4. So H1 is 3159.3 and H4 176.39. So it is coming 2982.91 kilojoule per kg. So this one is the heat supplied. So now we can also calculate the cycle efficiency for actual cycle. So actual cycle work done in actual cycle is 774.8 and heat supplied in actual cycle is 2982.91. So we are having 0.2597, or I can say 25.97 percentage. So 25.97 percentage. Now let's find percentage reduction in cycle efficiency. Percentage reduction in cycle efficiency. So the ideal cycle efficiency we are having 0.325. Actual cycle efficiency we are having 0.2597, divided by ideal cycle efficiency, that is 0.325, into 100. So we will get 20.1 percentage, that is reduction in cycle efficiency. So by this numerical we can easily understand, like if we are uh, familiar with calculation of quality of steam and how we can find out the enthalpy of mixture, and if we apply simple formula for work done and efficiency of turbine and pump, we can easily find out the values of unknown. Now let's take another interesting problem. So first of all I will write the problem here. So I am writing the problem here. A steam power station, a steam power station uses the following cycle. Uses the following cycle. Steam at a boiler outlet. Steam at boiler outlet is 150 bar and 55 knot degree centigrade. Reheat at 40 bar to 550 degree centigrade, and condenser at zero point 0.1 bar. Condenser at zero point 0.1 bar. 0.1 bar. Now, in this problem, we have to consider ideal process. So, assuming ideal process, find A, the quality at quality at steam turbine exhaust, quality at turbine exhaust. B part, cycle efficiency, cycle efficiency. And in C part, we have to find out steam rate, steam rate. So now let's solve this problem. So for this problem, I will draw the TS diagram for this processes. So it will be very easy for our understanding. So now I am drawing the TS diagram here. TS diagram. This one is the Rankine cycle with reheating. So here I am just showing the dome. Initially I am having a point 1, and from 1 to 2 I am doing the work 1 to 2s. I am representing S letter for the ideal process. So 1 to 2 is our expansion, and then 2s to 3 again is a constant pressure reheating, that is 2s to 3, and again from 3 to 4s we are having the expansion in the low pressure turbine. So now from 4s to 5 it is in condenser, and water is exit from the condenser at point 5. 5 to 6s there is a pump work, and from 6s to 1 there is a heat addition. So this one is a typical process for this problem, that is 1 2s 1 2s 3 4s 5 6s and again 1. So this one is the typical cycle on the TS diagram, that is Rankine cycle with reheating. So here I will show the pressure also. Here pressure is, that is here P1, we are calling it P1, 150 bar. Here the temperature is 550 degrees centigrade. Here again we are having the pressure, that is P2, that is 4 bar, and that is P3 condenser pressure, that is zero point 0.1 bar. So these are the typical pressure values here. Now from steam table I am just taking the values at the various steps. So now from steam table I am having the value of H1, that is 3465, this kilojoule per kg, kilojoule per kg. H2S we are having 3065 kilojoule per kg. H3, that is 3565 kilojoule per kg, and H4S, H4S, that is 2300 kilojoule per kg, and here X is X4S is 0.8. So in our previous problem we have already calculated the quality of steam. So same thing you can calculate, or either you can get from the steam table. So right now I am getting from the this value from steam table, but for get point of view better you calculate these things. So by equating the entropy you can easily get the quality of the steam. So now that is quality of steam at 4s point, and H5 here from steam table, that is 191.83 kilojoule per kg. So these are the values from the steam table. So now the answer of the part A is already coming, that is 0.88 we got from the steam table, but either by equating the entropy at 1 at 3 and 3 and 4s step, we can easily get the quality of steam. So now let's talk about pump work, that is nothing but VTP. So here we are having the value of V, that is 10 to the power minus 3, and we are having the delta P. Delta P here, so delta P, that is 150 into 10 to the power 2. So now we are having 15 kilojoule per kg. So this one is the pump work, and by this pump work we can calculate H6s, whatever we have calculated H4s in our previous example. Similar manner we can calculate H6s, that is 206.83 kilojoule per kg. So this is the value for enthalpy at state 6s. Now we are interested in heat addition. If you see this process, here are two kinds of heat addition. One is from 6s to 1, and second is from 2s to 3. So two times we are adding heat, so we have to calculate total heat addition twice. So for 1 to 6s we are having H1 minus H6s, and for 3 to 2s I am having H3 minus H2s. So now Q1 H1 value we are having 3465, H6s we have already calculated 206.83, plus H3, that is 3565, minus H2s 3065. So now we will get value of Q1 is nothing but 3758.17 kilojoule per kg. So that is the heat supplied, 3758.17 kilojoule per kg. Now let's consider the turbine work. So here there are two kinds of turbine, high pressure turbine work and low pressure. You see here 1 to 2s we are calling high pressure turbine, and 3 to 4 is low pressure turbine. So now we have to take these two work and we have to add it. So for 1 to 2s the work done H1 minus H2s, 3 to 4s the work done is H3 minus H4s. So WT equals to H1 we are having 3465 minus H2s 3065, plus H3 3565 minus H4s we are having 2300. So the net work done is coming 1665 kilojoule per kg. So we are having the turbine work. So we are having the turbine work, we are having the pump work, so we can calculate the net work done. That is nothing but WT minus WP. So 1665, and WP is nothing but 15 kg kilojoule per kg. So it is coming 1650 kilojoule per kg. That is the net work. So now we can calculate cycle efficiency. So the cycle efficiency is straightforward, W net by Q1. So 1650 divided by Q1, that is coming 3758.17. So we will get 0.4390, or we can say that 43.9%. That is the cycle efficiency. Here we are having W net, turbine work also. Now one more thing, steam rate. So we are having the work done is 1650, so we can easily calculate the steam rate. So calculating steam rate is very simple. We have to take 3600 divided by our net work done. So net work done is 1650. So we will get the value 2.18 kilogram per kilowatt hour. If you want the steam rate in kilogram per kilowatt hour, then you have to divide 3600 by W0. So by this way, we can get the steam rate value.